This is lesson 46 of the Quantum Mechanics, a mini lecture series, Schrodinger's equation, part 1. So there was a bit of a delay in the sense that I didn't talk about Schrodinger's work straight after the work of Heisenberg and Max Born and others. That's because I need to introduce some mathematical background first. So having gone through the maths, some of the maths, I can now go through Schrodinger's work. So Erwin Schrodinger was an Austrian physicist who didn't really like the idea of the highly mathematical abstract framework that Heisenberg and Max Born came up with, okay, describing the atom and the observable frequencies of light and so on and so forth. He wanted a return to classical physics. He liked the idea of this visual, continuous way of looking at things, okay? He wanted the electron to be a physical entity they can describe. And so he set out to develop another version of quantum mechanics, okay, which is now called wave mechanics. You can probably guess why. To describe electrons and atoms, okay, to explain their stability. And he was inspired by the work of de Broglie. So from before, we had this expression here. Okay, several videos back. Okay, psi, if you recall, that's the wave function. Okay, this expression describes the motion of a particle, okay, of momentum p and energy E traveling in the positive x direction, let's say to the right, okay? An electron traveling to the right. So Schrodinger set out to work out what equation this particular function is a solution of. So this is a solution to something, okay? It describes an electron in motion, okay, with some momentum p and some energy E. We need to find out what equation describes this, okay? This general equation that applies to all electrons. And we would need an equation. So Schrodinger believed that rates of change would be needed. Okay, things like velocity, acceleration. Okay, these are rates of change, quantities which require rates of change. Okay, it's all very dynamic at the quantum level. So let's take the partial derivative of psi with respect to x. Okay, let's square them. Okay, remember, so d psi on dx, that's sort of like a velocity, okay, velocity form. If you differentiate phi with respect to x, okay, with respect to the position, you'll get velocity. If you differentiate again, okay, which means squaring, you'll get acceleration. Okay, so Newton's second law of motion, F equals ma, involves an a term, acceleration, on the macroscopic, largest of scales. Similarly, perhaps the same thing would apply on the quantum level. Okay, it would require some sort of acceleration term. So let's find out what this is. So let's first start off by, I should say, just to make things easy, simpler, differentiating psi with respect to x. So from before, differentiating a exponential, okay, with respect to x, we don't worry about this term here, okay, we worry about this term here. Okay, so what's in front of the x? That's a k. Bring the k out the front. Keep the a, e, I to the, as it is. Rewrite it like that. If we differentiate with respect to x once again, if we bring down the k again, we have k times k, a e to the I, kx minus omega t. And k times k, that's just k squared, a e to the I, kx minus omega t. And I should say, apologies, there should be an I down here. Okay, an I as well. So then you have I times k times that. I times I is minus 1. So you have minus because, I'll write it down here. I square root of minus 1 times square root of minus 1 is just minus 1. That's the same thing as minus k squared psi, okay, because that's psi as we defined it up here. In the next video, I'll show you how to get the equation.